So today we're going to have two presentations on the FAST project, which stands for Faster Analysis Software Task Force. I won't say too much, given that I have the presentation. I think that you will probably describe a bit better and introduce properly the project itself. Okay.
I'll try.
So we have first Ben and then Lucas discussing two big chunks of the project. Thanks.
Are we sharing slides?
I think so. No, a second. Should be on. Yeah. Yes.
Okay, so yeah, I'll go off the Google Slides, but I'll try and give you slide numbers as well. But yeah, so hi, I'm Ben. I think a few of you already, but if you don't, I am still Ben. And so I'm one of the members of this team called FAST, and I'm going to show the first half of one of the main packages we've been working on. It's called Fast Carpenter. It's called Carpenter because it's responsible for turning trees into tables. So that's a cute name. The goals of what I'm going to show here, so there's sort of two broad categories. One is to basically present this tool, so Fast Carpenter and Friends, because it's really a set of packages, not just a single one. This is somewhat of a continuation of work I showed in last year, but a fair few things have been updated and improved. And one big point is it's not trying to be an analysis framework, though it might occasionally give that impression. The other two big points I would like to do is attract ideally some users outside of my local sphere, and ideally some extra developers if they were interested. And if failing that, I would very much be happy to see how this could be contributed into other similar efforts, because I'm quite aware that there are many other things that are very similar to this at the moment. And it's not a goal of this talk, but feel free to, if you have questions or comments, feel free to put them on the slide, and I can, if I don't get to them now, we can come back to them. I think that's one of the nice things about Google Slides. So on slide 3, just to say a little bit about FAST. It stands for Faster Analysis Software Task Force. It's a cute name, but it's perhaps a risky name because it means that we've committed ourselves to make good, fast software. What we are is actually a group of HEP researchers who are primarily based in the UK. We are physicists first and have our software engaged. Secondly, we started in May 2017, so we've been going for about 2 years. And our main sort of mode of work is the idea of these hack shops. So these are 1 to 3 day meetings where we get together mainly to test new ideas. And I'll come back to the very end slightly. But the goals of what we were trying to do was this was sort of in the early days with the sort of HSF white paper and so on. And so when we got together, we sort of had similar ideas in mind that we wanted to see how we could help simplify HEP analyses, increase the speed, knowing how much data we've got coming in future versions of HC and so on, and then tackle other things like how can we use automation and improve documentation in general. We are not related to the Fast and Furious franchise. I just wanted to put a photo in or an image in because software talks in otherwise can be quite dry. So just a note on the code base on where you can actually see all this sort of stuff. And this is one thing that's improved quite a bit since Chet. We are mainly using CERN's GitLab. The main advantage we found there was it's just easier to use the CI setup, and in particular that it plugs into EOS. So if there are files and things you want to host and access to EOS, that's very, very nice. I think for a lot of the packages I'm going to show now, and I think for Luke as well, there's no real reason why this couldn't actually move over to GitHub. And of course, the advantage there is we'd have greater visibility. For this talk, there's a demo repository that you can see, and a lot of the examples I'm going to give you come straight from there. So that's the second link from the bottom. And then the main package, the Fast Carpenter package, you can see in the link at the bottom. So just to give a little bit of context, this is where we sort of arrived at back in May 2017. On the top left is where we were coming from. This is what the analysis that a couple of us were involved in, and basically this had grown organically. It was based around a mixture of PyRoot, pulling in TH1s, TH2s, all sorts of different data formats were being passed around internally. It was quite difficult to manage. It meant there were very steep learning curves. It was hard to pin down and so on. And this whole pipeline was, as a result as well, relatively slow. And what we wanted to do is massively simplify this. And one of the ways we felt we could do this would be to adopt pandas, which is a very nice format for tabular data, columnar data, and sort of put this at the heart of it. And by doing that, we felt that we could likely massively reduce the number of data formats we had to pass around. But it was a general enough format that would be able to handle all the use cases that we had. And in addition, we felt that we could make things quite a bit faster overall. The times on the sides here are very, very rough. In fact, what we're showing on the side is much more. It's a goal, and we're getting close to it, but it's not. I'm not saying that's what we are doing at this time. So hopefully that puts you a bit in sort of the context of where I'm coming from. And in the big picture sort of sense, we were trying to sort of say, can we move away from asking how do I want to write a particular piece of code and get much closer to asking what do I want to see. So as an analyzer, you arrive, quite quickly set up the bits of the code that you need to write, but you don't actually get stuck into the details of how you're going to process it. So with that's enough sort of rambling. Fast Carpenter then is the point of this talk. And so in a nutshell, this is the main entry point for this code base, where we feed in a list of root trees, and then these will contain event level data, and we turn them into tables where we now have bin summary information. Again, there's the link to the GitLab, and then it's also up on PyPy, so you can see the link there, second link. Everything, as much as possible, is driven through YAML config files. The idea here is that these are very, very easy to read. In the same way that going from C++ to Python, you reduce brackets and semicolons, you remove white space. The YAML is almost easier. There's even fewer punctuation. That might be, some people might say it's a bad thing. Personally, I quite like that. And the other thing that I really like about it is it's very, very static. It's very, you can't write a for loop, you can't put any if else statement. I think technically it's not, what we have written is not strictly speaking declarative, but it's at least a step in that direction. And so this brings us towards this goal of writing much more what do I want to see and not how do I do it. And then one of the other big points is that this is intended to scale quite smoothly from doing quick studies to then a full-blown analysis. So these are the high-level sort of ideas behind this code, and I'll sort of walk you through the individual points. The package itself has a bunch of different dependencies. This is a big change from where we were in CHEP. So this now uses uproot to read in the files and turn them into arrays. And occasionally we are still using pandas internally, but we're actually moving slightly away from that now, at least for some of the real internals. Alpha Twirl is a package developed by another member of the FAST team, Tai Sakuma. At the moment, it's mainly used internally now for multiprocessing and the support to interfaces to the cluster, so ElixBus or HDCond or SunGrid Engine on some of the other sites that we have access to. And then, in addition, this is all connected up through Pandas Orchid Array, and I also interface things a bit to NumExpress. Then there are two packages that plug into all this, FastFlow, which helps to actually interpret the processing config. So the idea is you're defining this is how we actually translate the flow of the data, and then FastCurator, which helps curate the libraries of the data set and so on. So the naming is hopefully somewhat informative as well as huge. So let's really get into what this would look like. The first bit in your config file is the processing configurations. How are you going to process your data? What are you actually going to do with it? Currently, the config file starts with a section called stages, which is basically just a sequence of steps so that you're going to do. I say it's a sequence. It's probably not strictly right that it is a sequence, but it is at least thought of sequentially. And this is something in the future I'd like to move away, that it makes it easier to have something less sequential and potentially more of a full directed tree, but at least for now, this is what it looks like. Each stage in here, the only requirement on it is that it's a Python importable class. So this already gives you an entry point to bring in your own classes if you need, but we provide a bunch of standard ones. So you can see on the left here an example of what this would look like. We're going to have for this processing, there are 5 individual steps. The first one is going to define a bunch of variables. The second one is going to use a custom stage that we have to write specifically for this analysis. Then we're going to produce a bins data frame on the left, called referred to as number muons. Then we're going to apply a cut flow, so we're going to select some events, and then finally make another histogram on a different set of variables, having removed some of the events from before. So this is just one example. Hopefully you can see how this works. So the key in these, this is just a list with a single length, where each element is a single length dictionary. The key there is the name of that stage, and then the value is the type of class that it's going to run. So next on slide 10, so that first step, defining variables, So here we're combining, I brought together sort of uproot and NumExpr. This is version 2 of NumExpr, so there's some extra stuff in version 3 that might be interesting, but at this point it's NumExpr 2. And this basically, the interface we have here, it presents up the uproot tree as a dictionary to the NumExpr parser, so that when it passes the expressions that you see on the in the config on the left, when it finds a variable, it will ask at this dictionary type object, do you know this variable? And if it's in the tree, or if it's a variable we previously defined, then it will pass that back. The other aspect that we have to handle is the jaggedness. So if an array comes back from the tree and it's jagged, we have to do some manipulating to make sure that gets passed in and passed back and wrapped back up into a jagged array afterwards. At the moment, there is a requirement that every variable that you mention in there has the same jaggedness. But it's quite natural that you can imagine in the future we go to something like NumPy, like broadcasting, that we would have to handle, which we don't have yet, but we can think about how to add this. On top of that, quite often we'll want to reduce these things, and there's no natural way in NumExpr to do that. So you can see an example on this config on the left here, n-isomuon. It's going to take, the formula here is just isomuon index, which is the second variable defined up here, and now it's just going to count the number of non-zero. So times that returns true, and that's basically going to give us the number of isolated muons in this analysis. So this is a reduction because you're counting number 0. You're basically taking a jagged array and reducing it to an array where it's one element per event. And then finally, you can see how this same thing works now on an event level array. If I click that, is it going to? So then this last guy here, this is an event level object where we're again applying the same cut. So as well as interfacing to NumExpr, I'm also doing a bit of butchery to uproot to be able to add these variables back into the tree and present it to the tree. So uproot really does think it's part of its tree. Meaning if you now query the uproot tree for a pandas representation of your data, it can handle it. These new variables are absorbed into that. And that's basically achieved by mainly butchering the values method. It's quite, having you in the room, Jim, so yes, so that's how this sort of works and looks like. The next sort of stage that we might want to do is now fill a histogram. And so the configuration of these, you've got quite a lot of flexibility here. You can specify how you want to weight the inputs to there. You can have multiple input weights, i.e. you could say don't weight it. In fact, sorry, every histogram comes with the unweighted number of counts. But if you specify a weight variable or a list of weight variables, or even if you want to provide a weight variable that changes name, we handle that. So you see two examples on the left here. We specify weights. We give a list of individual weights, or we use the mapping version where it's basically going to rename this in the outputs. Then we have to define how we're going to bin. So we can either assume that a variable is already discretized, in which these top two here are an example of that. The number of muons is a discrete variable. We don't have to worry about binning it. You can define equal width bins over a range. This is quite similar to standard root format. Or you could provide a list of bin edges. There's a special case, which is mainly there because it massively makes things more efficient, which is if you want to just bin on the dataset name. So when you see dataset call is true, that's what's going on. It's going to add a column to bin on that dataset name. And at the end, what you get out of this stage will be a bin data frame, which will on disk look like a CSV file. It goes through a pandas step, and this is an area where in the future, very near future, I would like to swap this to a GAST. So that I think that should be more efficient, and it might be easier to then interchange this with other packages. This is a good example of where
I can tell you what that means.
I will say yes to that.
Okay. So, can I ask a quick question on that last slide, the fill a histogram slide?
Sure.
You have, like in the binning, an in and an out. What does that mean?
So I think actually out is no longer necessary, but when I put this example together, it was. And basically, it's a rename. Okay. It allows you to, if you don't like the variable that's in the tree, or if you've got maybe many different trees.
So this basically labels the column of the CSV file.
Exactly, yeah.
Okay, perfect, thanks.
I think now it's not actually necessary. You can just say in, and it will just, of course, the out is the same as the in. But I think when I wrote these examples, that wasn't the case.
But dimuon mass is also a name. How is camel case dimuon mass related to underscore based dimu mass?
The camel casing and snake casing, whatever, it's not affected at all. So in the out, maybe it's misleading, but out doesn't mean that the variable is now added into the tree. So future stages don't see that variable. It's just that in the CSV file that's produced in the columns, it now has that name.
Yeah,
that makes more sense.
But in the CSV file, if the dimuon mass colon.
Mm-hmm.
Okay. Well, that first one there, I think, isn't that just a stage name? Does that depend?
Oh, you're asking about here.
Yeah.
Sorry, yeah, that's just the stage name.
Because that could be used as the column name.
Well, in principle, you've got, so here, for example, you've got multiple columns. If you've got a single column, maybe, but I had...
The output name.
Well, how would you handle it if, so here, for example, the stage name is number of muons, but there are 2 columns in the, well, 3 if you consider the data set, if you see what I mean.
Yeah, right. I mean, as the exported name, not the import, not selecting which. So not to replace in, but to replace out.
I appreciate, but then there's 2 outs in this example.
Because it's two-dimensional.
Yeah.
Okay.
Maybe in a one-dimensional case you could do that, but,
Okay, yeah.
but the name, so actually, well, if I go to the next slide, is this going to work? What? It's just a PNG. Come on, Google. Okay, I'm going to, for some reason it's not rendering the PNG, at least here. Maybe, hopefully you can see this.
Speak enough.
Yeah. This is what so we've now dumped that out after the run, and then I've loaded it back in. I've loaded it back in using pandas, so it's just read CSV, and then it's just a nicer way to print it back out. But maybe to answer your question, Jim, a little bit, the name of the file that's produced doesn't actually include the name of the stage. It's based on the name of it's a structured name in the field of the file, and then contains information about the columns and the weighting and so on. Anyway, so now we see this back in. So you see we've binned it on the dimuon mass, and we had the dataset column as well. So you now see this. It's actually a 2D histogram. There are 3 columns containing values. So the first is the unweighted counts. It's just n, and then the next 2 columns are the sum of weights, where the weighting scheme is just weighted, and then the sum of weights squared. And so this is our way of representing binned histograms within Fast Carpenter and so on. And I think this should map quite nicely onto things like Agast. I mean, this isn't coincidence, because when I was putting this together, we were talking, yeah. And I should just say that this is not the full CSV that's produced. I'm only showing the first 3 rows of every data set, and this is a small demonstration of why Pandas is nice. It's very easy to do this. Show me the first 3 bins within for every data set. It's one line with a group by operation that you see up here. Okay, I'll go on. Can I go back to the... so just slightly technically, I should be careful with time. Okay, I won't spend too much time on this. This is more technically what's going on behind the scenes. This is one area that's very, very unoptimized at this time. It's one generic function that can handle all the use cases, regardless of how many variables you want to bin on, regardless of whether one is discretized, one is one needs binning, regardless of how many weight schemes you want to apply. It's a single function, and basically it benefits from Pandas. Again, Pandas interface, it's very easy to write a generic function like this, but it means that it's not very optimal, and there's obviously Henry's nice demonstration of better ways to do this, so this is something I'd really like to do. What is nice is that because we have this config file, analyzers don't have to change their code at all. We can just do this all behind the scenes, and we should see things much faster. So the next stage is an event selection, and so this is how this works. There are two examples here on the left and on the bottom right. The point is that this is going to mask out events from subsequent stages, so that they no longer see the events that are in the tree. This also will produce a cutflow summary, so in there you will see the raw number of the raw counts and weighted yields. So again, you see we're specifying a weighting scheme for these stages. and those yields will be both inclusive and exclusive with respect to the other cuts. So it's very nice if you want to really understand your cuts. Just from this, it's pretty helpful. We've used it quite a bit in our analysis. The selection, the way this actually works, so it's just a nested set of dictionaries, and all. If the flag is all, then it's basically the and between every subsequent element in that list. If it's an any, it's essentially an or between every element in that list. And each element in the list is exactly the same as the variable definition stage. So again, it's going back to using nummix for, we can reduce, so this here is going to take the leading leading muon, sorry, the muon with the, well, the first muon in the list, I suppose, is the better way to put it, and check that PT is greater than 30. And so on. I should give a little bit of this sort of idea of nested dictionaries actually came from Alpha 12, which was put together by another member of FAST. And so yes, this is how you would go about controlling these cut flows. This is another example of where, anyway, this is what the CSV file that you get out from this looks something like this. You can see the data set, you can see the cut that you're applying, and you can see the number of events passing each cut, both weighted and unweighted, and inclusive and then exclusive. So how many events pass and how many events were fed in total. So you can really look at the efficiencies of these cuts. I will continue. And then lastly, are those custom stages. So I've tried to present, what I've tried to build are like the key stages that you would really need, but obviously there are some cases that would be very hard to fit into all of this. And in that case, you do have the option to write your own custom stage. It will, it's fairly easy to import this because you just specify that in the beginning, in the stages section, you just specify the Python module that it will come from. And the only requirements on the interface is that the main one is that they will implement this event method that will be given a chunk of events, and there you should do what you want. You also, if you want to collect information and write it out the disk, you have a method there to do it. It's straightforward. It's not too different to many other sort of frameworks in that regard. And if you want to see an example of this, you can click this link, and that will take you through. So that's how the Fast Carpenter sort of processing will go on. Once you've got those data frames, you want to make those into plots. And so here we have a new package called Fast Plotter. I don't actually like this name that much, but it works. It does tell you what it's doing. The basic sort of philosophy that I've had here is that you want a very easy way to just turn those data frames into plots, and they should look roughly good. But when you then want to go and tidy them up and make them really propagation quality, then we should be giving you the small functions that you need to do that in a dedicated script or a notebook. The plot on the right is what we produce just from the single command on the left at the bottom there. So in my opinion, these are actually pretty good quality, given that you're not doing much configuration. I've hidden some configuration in this YAML file, but basically it's adding the labels and making sure that the legend doesn't overlap. All of the coloring, all of the error bars, all of the ratio plot is taken care of for you. And I hope that what I've done in here will map nicely onto Agast when and if I transition to that.
Plotting is not related.
No, but I'm hoping that the manipulations I do internally to make these plots should be straightforward to adapt away from pandas to Agast, the Agast input. Whether I go via pandas indirectly or what, I don't know.
What are you using for the plotting?
It's matplotlib, but it's
Okay.
and mostly it's well, I do a bunch of manipulations of the data frames. There is a couple of plotting steps that use pandas interface to matplotlib fairly directly, but there are a bunch of others that I write myself. For example, here this is a fill between, and I call that on a group by over the data sets, and then and then apply on that. Briefly, so one thing I haven't sort of touched on is how you actually describe your data sets, and this is the Fast Curator package. This is an area where I think it's we transition quite nicely from doing quick studies to a full analysis, because it's just these input files grow, but the actual processing files don't. They don't change. And these input files config files look like this. So there are three key sections. One is the main one is the data sets. section where you describe the list of input root files. There are some metadata attached to this, such as the name you would like to call this dataset by. You have a default section, so you don't have to put all of these variables in all of the dataset sections. And then in order for you to simplify this, so if you have very large datasets with hundreds of files in a dataset, there's actually an import mechanism that you see at the top here. You don't need to generate these entirely by hand. There is a command line tool called Fast Curator, and there you can wildcard. So if, for example, you have a bunch of files in a directory, you can provide that to the command line tool. It will expand the wildcard and write out the YAML file that you see on the left. This can then be stuck in your repository, and every time you get an update to your input files, for example, you can see very easily the changes in there. This globbing also works over XRootD, as long as the directory on XRootD has the right permissions enabled. And I've got a PR open to the actual Python bindings to add that into official XRootD. So it's been sat there for a few months.
Relevant toward this, I heard something about that. This is not an XRootD. Well, the following, which I'm going to say, is not an XRootD limitation. The way that the sites are set up, sometimes you can get data from a site that it won't list, because when you ask for data from that site, it goes and gets them.
Mm-hmm.
So even if you have the feature for XRootD to glob and list your files, that would be underrepresentative of the files that are actually there. So if you go to all the work to get that done, it might not be helpful.
Well, so the work is done at least, and it seems to be working on the one. So it doesn't work, for example, using CRAB for jobs that are stored in CMS, for files that are stored on the in DAS. It doesn't work there, and I believe it's a permissions on the directory that you can't, like wildcarding. It doesn't work there, or well, the functionality I need to inspect a directory. However, for the I think files that I can access through EOS more directly, there it does work, or on other storage elements where I have access. So there it really does work, and I've been able to confirm that it's a full list. So you might be right. Maybe it's a bit dangerous actually. If that's
so there are ways to ask an XRootD redirector to recursively search all child XRootD servers for files. You would have to go to, say, the global redirector and do this query instead of the specific node. But in general, I don't think this is a great direction to go, because it puts a lot more load on all of the XRootD redirectors, where all the metadata you need to know is already available in services such as DAS. Sure.
So what I want to do here, how we've been doing it, is we query DAS, we get the list of files, and we bring that into this. It means that there is a hook in this package that you can use we will interface with. We haven't done this, but that it will be able to do the DAS query for you and then expand it into this format. For files that aren't on DAS, like private, this has got very CMS specific, but for private production stuff that hasn't been published, for example, this seems quite nice. But
and it's also practical for that case, because you'll know that all these private files are at a specific site, and so you can directly go to that site.
Yeah.
And then it's very reasonable to do this sort of recursive query because it's within the site.
Maybe I could ask one of you to add a mention of that on the PR as well as to just push it along. Okay, I'll move on from this because I'm quite conscious of time. Anyway, these are all the packages I've shown you. I've gone through Carpenter, I've gone through Plotter. I mentioned FastFlow, which actually handles the configs, and Curator, which is the last slide. I'm not at all going to touch on this guy. This is sort of an interface we had to some fitting stuff, though we have to see where that moves to next. And then just the next talk from Luke will focus on this validate package. So this is the sort of interplay we have within these tools. Obviously, a good question, especially as our name is fast, is just how fast is this? And so most of the examples I've shown you, all but one I think, are based on a C++. There's a CMS public tutorial for HEP analysis. It's largely based on root. It's C++, and everything runs on a single core. So everything I've tried to do is to reproduce that analysis. And so our code takes about 6 seconds to run over that. The C++ example takes about 3. There's a factor 2, which is not very nice. Most of that is coming at the very end stage, but I think there's lots of stuff that we can do to improve this. But one thing that I really do think is nice is how you describe that analysis and the number of lines of code and the readability of it and so on. I think for me is I like. I'm totally biased there, I appreciate it, but I like it. And I do want to point out that I do want to stress how much this is right for optimization. So we have the histograms that we're producing. It's a function that's very general, but it's using pandas, which both means because of its generality and the fact that it has this has to convert into pandas format means it's relatively slow. It could be optimized. At the very end of the job, when if you've multi-processed things on the batch system or whatever, there's a big bottleneck of then combining these together that we could improve on. And I don't do any caching at the moment. So if you reuse a variable definition, maybe you take the first object and then compare it to the second object in an event. For example, that would have the same equation, and there's no optimization at all there for those sorts of comparisons. One thing I just want to very quickly flag up is that all this quite nicely fits in a GitLab pipelines for this, at least for the example tutorial that I'm showing. This means that this is one of the ways I'm validating these tools now. Every night this reruns, it collects the input data from the public source, rebuilds that file list, regenerates the bin data frames and the cut flows, and then turns those into plots, and you can see all of these outputs in the you can keep these artifacts are now in the pipeline, and in principle this could then be published as a PDF back to to some repository somewhere. This is why if you're going to build this is why we liked GitLab in the first place, because this could, for example, publish back to EOS. It could be pulling files from EOS in principle. So this is really nice. I really don't know if this is any way sort of realistic for a full analysis, but it can happily manage on a subset of your analysis to test, for example, that things are running. And so this sort of brings me towards the end. Going forwards, there's lots of things to improve, principally documentation. This is one of now the main sources of documentation, as is the example repository, but there's not much else beyond that at this point. There's lots of optimization to do to speed this up. We have a couple of ideas for new tooling. So, for example, how can you optimize the cuts in your cut flow? We have clear ideas how we can do this just by having a large multi-dimensional bin data frame. It's not too difficult to envisage how you would go to a bin improvement or optimization of the cut flow. There are some new tools that we would like to replace the internals with. I mentioned the gas. There's a discussion of how to plot using a new package, which might be nice to include. And I would at some point like to move towards something else behind the scenes for the concurrency. And I mentioned this right at the beginning, but I know there are similar efforts elsewhere. And if there's any interest to work together, or take these tools, move them into that, work the other way around, it'd be nice to have that discussion. So that brings me to the last but one slide. There's one after this, which is that clearly the code base, if anyone does, maybe no one does. If anyone remembers the talk from Chet, we've moved forward with it all. The whole analysis is primarily YAML based, including the data set description and how you want to process it. That makes it largely declarative, though, so you can optimize things behind the scenes. Though we do have ways for you to inject custom stages. At this time, it's about twice as slow as the equivalent C++ analysis, all using a single core. There's lots of low-hanging fruit to optimize this better. All of the tools I've shown are on GitLab and on PyPy, and you can see the links there. And just finally, I mentioned right at the beginning, the way we worked to develop these tools were what we were calling hack shops. They're somewhere between a hackathon and a workshop. So you basically bring a small group of people together for a couple of days, and then people, either on their own or in pairs, will sort of work on a project they've defined. It was a great way to try new tools and experiment with new ideas. And so far, we've had about four hack shops over the last couple of years. And we will, I'm curious, is this something that would be interesting to people? Is it something we, if we put something together like along these lines and specific to something like the plotting or adopting a GAST or whatever, would that be interesting? And that is my last slide. Thank you very much.
Thank you, Ben. The answer yes. Any more questions?
Good talk.
By the way, a few questions. We'll still have time for one or two, I guess.
Hi, here's Peter. Can I ask a question?
Go.
How this compares to the root R data frame in expressivity? How many lines of code you will have to write, and in speed?
It's a great question. I haven't done that test. I've ended up focused on this, and my analysis is sort of using this approach at this point. So I'm not finding time to sort of do that. But I would not be surprised if that is faster by a reasonable way. I'm not sure about the expressivity. I personally, well, again, I'm totally biased, but like something like YAML, I find very, very easy to read. There are no, there's no punctuation, there's no loops and so on. And so at that level, I imagine it might be easier to read, but I cannot give you a fair comparison. What would be interesting is to do that, sit down with someone and.
But when you want to do, for example, in the selection, if you want to do a complicated expression which involves calling functions and so on and so forth, can you do that?
Yes, yes, because so depending on what the function is, yes, you can put any arbitrary any equation or expression you can think of would fit into this, provided it meets the current criteria that the variables you manipulate have the same jaggedness and so on. If you wanted to do something more complicated, you could introduce your own stage, you could implement a custom stage. And so at the moment, yes, you have total scope to do this. It might not be as neat, it might not be, if you have to introduce your own custom stage, it might be extra work. And it ruins some of the declarative ideas behind this. But it's possible, absolutely it's possible. And personally, I find this, I really like the way that this looks, this selection, the description of this cut flow. Okay. And the thing I really like is the cut flow table that you get out at the end is super useful. The fact that because these manipulations are vectorized like this, it's very easy to do both the inclusive and the exclusive cut flow efficiencies and to do them weighted and so on. So that's been really helpful for our analysis.
I just wanted to say, taking a step back, one of the big things that C++ does to us is boilerplate, which is exactly, I think, what you're talking about, why you like YAML so much, is you, in just a few lines or characters, you can express tens of lines in traditional C++. And you had that great comparison at the end of comparing the standard CMS example analysis to how many lines of code it took you to write. It was like a factor of 2. And my guess is with some more work, you could get even better than a factor of 2. The danger, of course, is that, in a language like YAML, that's not, as you were just saying, it's not turning complete. So when you need to do something special, you often have to drop down to, say, Python or something like that, which of course adds more boilerplate, but also adds more capabilities. And one of the things with all of these projects is finding that sweet spot where you want to exist that removes enough boilerplate but keeps enough functionality at the same time. Or you end up having to do multiple languages, which I think is the route that you've taken for now.
Yes, I totally agree with what you said, and I think the way I sort of envisioned this going was, once we have a better understanding of how analyses would be using this tool, if there are common use cases like forming die-object variables, that's one that we often end up doing, where at the moment we're writing a custom stage. That could become a core part, which then you are back only using the YAML. Another common one is like lookup tables. I mean, I'm aware, I've followed a bit the RDataFrame discussion. I think I'm describing things that RDataFrame have also been coming across, like a lookup table, so you can produce event weights, for example, is a common thing. All of these things, there's nothing to stop us. Once we have a better understanding of what those individual requirements are, making a stage that then sits in Fast Carpenter or wherever, and then the user no longer has to write that. It's back to being something we can take charge of optimizing. So my sort of idea here is it should be easy to do easy things, and then if you need to do something more complicated, you do have the option. And then as we use this more, we would integrate the hard things back if it's a common task.
One quick question. In these stages, so this is where, for example, you can have input from other files that are not the data specific, some calibration files, for example, that are going to change some of the leaves of some of the variables in your tables. That's perfectly viable.
Yes, essentially. There's no stage in Fast Carpenter at the moment that does that for you. Mm-hmm. But you can write. We're doing this. We reweight by pileup or reweight by mm-hmm. PT and eta bind jet corrections, that sort of stuff. That lookup table is just it happens in a pandas data frame, and it's a very simple case to just to use that as a lookup table in your custom stage to produce a new variable based on the whatever, the JPT or phi, whatever. And that's clearly a common use case, so it's one of the things in my mind that should become a core part of the fast carpenter.
Okay. Thanks. If nothing pressing, then I think we should just move to the next talk. Right. Lucas, will you share your slides, or we do it from here?
If I can find one of the many screens that the slides are currently on. There you go. Can you see them?
Okay. Yeah. Please go ahead. Thanks.
Oh, fantastic. Well, first of all, thank you very much for the opportunity. The prelude of this talk is basically similar to what Ben has shown at his, so skip all that and jump right in. So scikit-validate. So first of all, I want to clarify the validate part, because validation tends to mean different things in the computing context, right? So here I mean specifically the verification of observables whenever you make a code change, right? You want to verify if, after a code change, physics change in the way, or some observers change in the way that you expect them to, or they don't change at all because you didn't touch, the code relevant to it. Now, big experiments put a lot of effort into physics validation for their software. For instance, having huge Jenkins setup that are run for every merge and pull request. Now, the problem, of course, is if you have just a few handful of scripts, or if you have a very small analysis framework for your group, or what about small experiments, right, that don't have the person power to actually set up this full-fledged validation system, right? And although you don't have the person power to do that, you still need this validation, right? You want to have scientifically reliable results. So this project essentially started from a set of scripts from a CMS analysis, as well as from like Zeppelin simulation. So the package itself comes in two parts. First part are the observables, so basically stuff you want to compare to a reference. This includes, but it's not limited to values in the root tree, for instance, literally the stored values. Can include a breakdown of where your data storage actually goes into, like the 10 biggest consumers in an ntuple. Things like high-level observables, so something that is not stored in a tree, but you have a derived variable that comes through it. And then you have stuff like generic metrics, like performance measurements, so CPU, time, RAM, file sizes, and so on. And maybe you want to keep track of any kind of code issues that appear, or software versions that are used for specific builds. Now, on the other side, of course, putting everything together, you want a clear kind of answer to the question, has something changed, or have things changed in the way you expect it to? So the reporting side of things basically will summarize all the metrics produced, kind of the outcomes of the continuous integration pipeline, as well as any kind of validation outcome. So if, for instance, a mismatch between distributions occurs, it will show you, oh, this is the distribution, this is the mismatch, and show you a plot. And of course, kind of summary for the generic monitoring side. So because this is meant to run in continuous integration, much of the code is exposed via commands. And here I'm kind of highlighting 5 rough kind of areas where these fall to. Some of these commands do not exist yet, so they're highlighted with a star. And essentially you have the set of commands that do the comparison, a set of commands that do the performance and resource metrics, kind of the out-of-the-box wise at least, checking the environment, like detecting software version, which root version, Python version, etc. And then stuff that produces actual reports, so Markdown files or HTML files or PDFs that you can then download, and some utility functions that you can integrate in your CI. So although the out-of-the-box functions you can easily compare two root files with each other and will give you output. Sometimes you want, to have an access to the high-level variables. So I wanted to kind of give you an idea how, from an analysis perspective, you would do it. So going from left to right is kind of how the script that produces this variable is structured. So first of all, you actually read in the tree, you do some computation, which is the middle bit, and then on the right-hand side, you write it. And essentially, what you write are arrays of some sort. So there's an example of the XY shown here and the histogram. So this is a very minimal example, but of course, you can do much more than what is shown here. So when you then compare the files, so this is comparing the previously mentioned the X variable, you have them stored in two files. So one is your reference file, one is the file that is produced for this particular code change that you want to compare to, and what you get out is what is shown on the right, essentially comparison between the two distributions, which includes some statistical evaluation. But essentially, since these are kind of expert level distribution, whenever a difference is shown, it will display, for anyone to check what's going on. And the results of this evaluation are stored in the JSON file that then can be used for further processing. So some of the commands provide you kind of with general metrics. So for instance, execute with metrics, then command name will create the JSON file shown on the left. So it will just basically note how long it took to run, which value is better. So for instance, faster is better, so lower number of seconds and so on. RAM usage, and on the right side you have the kind of file metric, just essentially file size. And smaller files sometimes can be better. And of course, with the similar kind of structures, you can see with specifying the metric name, value, unit, and which one is better. You can add any kind of metrics to the mix that you want to keep track of. Now, all of that is fine. You can, do your comparison and so on. But the kind of more important side is on the reporting to kind of summarize information and make it easily available to the analyzers to then make decisions. So in order to kind of create these reports, the current implementation relies on Jinja templates and YAML configuration. So basically, the templates are used to define the structure, so the markdown, PDF, etc., of the report, and defaults are provided. And the configuration then describes how templates are filled, and again, examples are provided. So of course, you can add your own code in a similar way that Ben has showed you before, where you just specify kind of the function that is called to fill a particular input. So you can see it, for instance, on the bottom left. Oh, you can actually see my mouse, right. So for instance, for the output URL, which is a variable in the template, a function is called that you specify like this. So essentially, any kind of Python function that you can call, you can pass to then produce the output. And yeah?
About that templating, which is applied first, the template or the YAML?
Well,
and the reason I ask
it depends. So in this example, a first application of the template. So the example config file you see here already includes templated values, right? Which is something, for instance, the scikit validate bit that you can see here, or the output file, right? So if an output file is specified, or the default. So first, this is run through, rendered as a template, and then the YAML file is read in, and then the final markdown is produced. So that's the order.
Right. So the reason that I asked that is because in that order, a template can get out of can run away. Whereas if instead the YAML is done first, and then you apply templates to each key and string type to value of the resulting JSON, dicts and lists and such, then it will be somewhat safer because the templates would be confined to whatever key or string typed value it's in. Like just making these macros more hygienic.
Okay, thank you. That's useful. Okay. So to continue, so in this example here, you have a keyword called section. So this is what's used to define the different sections in the Markdown, as in the different headers, if you so want. And these you can put one section into another. So you have on the right-hand side the kind of section example, which would be the performance report. So here again, you can specify templates, specify the metrics, how they filled, where the JSON comes from, and some symbols. If you want to kind of customize the up and down symbols, you can do it this way. And of course, this section can have further subsections and so on. Now, if you just want to run the defaults, kind of a demo report is provided in the repository, which will create a report that is shown on the right. So you have a pipeline summary, which basically in the real life scenario would read the pipeline that the report is produced with and give you kind of a summary of what passed, what didn't, and which, for instance, software versions were used for the different jobs. It will also give you, actually, on next slide, the validation report. So first of all, you have here at the bottom the summary, which kind of shows you, oh, did you find were any distributions found that differ? If yes, which ones? And if you click on details, you get this the kind of summary, detailed report, which in the detailed report looks kind of like this. So essentially, you have each of the contents of your root files then produced line by line. If basically if the success criterion has passed, then the plot will not be shown and just marked as success. However, if the criterion that is set fails, then it will show you the plot and for human evaluation. Now, the last bit is, are the performance and file metrics. So here again, you get a bit of summary. So first, the disk size report on the bottom, you have the kind of different files that are analyzed and kind of showing you, the value and reference value and where the difference in which direction it goes. And it's very similar for the performance report. So even if you had, for instance, custom metrics, as long as they fit the same format, these tables can be reproduced and basically reusing the code underneath. Now, all of that is good. If you don't do anything, essentially these reports will be only available as artifacts, which means if you have a look at the pipeline, which looks most like this, it's very difficult to actually get to them and find them. And we found that especially for newcomers, they have really trouble finding this additional information. So what we decided to do is then actually, the usual workflows is to actually create merge requests, then the pipeline is run. So we can actually use that fact to display the results back into the merge request. Right. So for project maintainers, it means that they would have to set up a read-only API access. For now, this is only available via a bot that essentially has just, for safety reasons, read access to the repository. There is a GitLab issue open for that. So, for read-only API access with deploy tokens. It will be then added to the token should be added to the CI variables, and then you can use the submit report to MR command to feed back the reports to the merge request, right, which solves the visibility issue. Right. So to summarize, I hope most of you are aware that validation is an important ingredient for reliable reliable scientific results. And the aim of this kind of scikit-validate package is to provide a minimal set of tools to ease the validation efforts for small projects, say individuals, small groups, but also experiments. And it allows you to easily compare kind of root files, also to capture metrics, and provides you automatic reporting in the GitLab continuous integration. Now, the features that are in there are essentially problem-driven, right? So, as I mentioned at the beginning, this is kind of a merger of scripts used at CMS and at the Zeppelin experiment. And it has gone through a few iterations where only the useful things have been kept in so far. So it is used on a regular basis. Sorry, it is kind of the validation side of things for the LZ experiment. And the plan is to make this a bit more configurable. So the definitions of what how is success defined for the validation, what is a failure. At the moment, it's a very simple metric that might not suit everyone. But if you're interested in this, please give it a try. Simple pip install will do the job. Any questions?
Thanks very much. Any questions maybe from outside first? Or comments? From the room? Anybody? Any question or comment? You said this is running the LZ experiment. So I guess this is not on GitLab, is it? Because you mentioned integration with GitLab, so now I'm confused. How is it being used then?
So it is on GitLab.
It is on GitLab. Okay.
Yes, the LZ experiment has its own GitLab server.
Okay. Okay. So it's not a certain GitLab. All right.
No.
How big is it at this stage, and how can it scale? I mean, how many? How large is the report size that you have at the moment? How many kind of checks do you make?
So for the demo, it's fairly small. For LZ, it can grow quite large. For instance, we don't produce the PDFs for LZ just for that reason. Sorry, I don't know the number off the top of my head, but it's a few megabytes.
No, it's large, yeah. Okay. So this is more meant for, but you're targeting analysis or code development or monitoring specifically, or just in general anything where you can compare, say, histograms?
So, fun thing, it actually doesn't compare histograms. So it only compares T-trees for now. So yeah, it is meant to be fairly general, and we've been using it as Z simulation and CMS analysis, but yeah.
Yeah, simulation is another one. Yes, good point. Okay. All right. Thank you. No, man.
Maybe how do you want to talk about the GitHub stuff, Luke? Is it to do the same to the stuff for GitHub?
So the issue is actually with GitLab, right? So it's much easier to set up these things with GitLab than with GitHub. So this is why, and because LZ is on GitLab, this is why we've prioritized it, right? So there is no particular reason why you shouldn't be able to do this with GitHub. The API, to do most of the things exists. We just haven't had the time to actually explore that option.
Yeah. Yeah. Okay. Anything else? No. Otherwise, we're just on time, 1 hour. Nothing else. Okay. Thank you very much again, Ben Lucas, and we'll keep in touch for anything anyway.
Yeah. Thank you very much for your chance.
All right, thank you. Bye-bye.
Bye.